All right, so now we've talked about how we can visualize a multiple linear regression model, both for when we have the case of having a quantitative and a categorical explanatory variable, as well as having two quantitative explanatory variables. So let's talk about how we can fit these multiple linear regression models in R. So fitting a multiple linear regression model in R is a pretty simple extension of fitting a simple linear regression in R. So let's go ahead and refresh our memories as to how we do that. So the first piece when we're fitting a simple linear regression model is we're using this LM function, which stands for linear model. The second piece is the response variable that we have in our relationship. So here we're modeling the course evaluation score. And this squiggle can be said is a function of or is being modeled by. And our second piece here is the explanatory variable that we're using. So this is the average beauty score. The next piece is the data set where those variables live. So these both live in the evals data set. In this chapter of the Modern Dive book, they introduce this get regression table function, which lives in the Modern Dive package. It allows for you to input a linear model, and it gives you this nice, tidy regression table. However, we don't actually care that much about these other pieces of this regression table right now. The only main pieces that we care about here are these estimates, so we could equally do the same thing using this coef, which stands for coefficients, function that pulls off the coefficients from our model. So we see here's our intercept coefficient and here's our slope coefficient. So this is how we go about fitting a simple linear regression model. When we think about fitting a multiple linear regression model where we're allowing for there to be different lines for our different groups, when we're including a categorical variable, we actually have two different modeling choices. So the first modeling choice is what we saw before in the data visualizations, where we allow for there to be different slopes for our two groups. So we also allow for there to be different intercepts for our two groups, but that's not as important. So here we're allowing for there to be different intercepts, but notably each of these lines is allowed to have a different slope. So the relationship between average beauty score and course evaluation score for female professors is allowed to be a different relationship than male professors. If we thought that the relationships look similar enough that we could have modeled these slopes as parallel, that is what we see in this parallel slopes model. So in this model, we're assuming that this relationship between the average beauty score and the course evaluation score looks the same or approximately the same across the two sexes of professors. And really the only thing that's different is this shift in the intercept. So we see that on average, for the lower or for beauty average scores that are lower, we see that male professors on average have a little bit higher of an evaluation score than female professors, but we're assuming that this relationship is the same. So we could say that this parallel slopes model is actually the simpler model. This different slopes model is the more complex model. However, transitioning from one model to the other requires for us to look at the visualizations and decide if it seems reasonable for us to assume that these slopes are parallel, and here I would say that that's not a reasonable assumption. So let's walk through how we model each of these two different choices. So when we fit a parallel slopes model, the only thing that we add to our original model is we add this plus sign, which means and. We're also including this other explanatory variable, and we add on the sex explanatory variable. So that says, I want to model the average course evaluation score with the average beauty score and the professor's sex. So if we pull off the model coefficients of here, we see that we have our original intercept, we have our original slope, and the only thing that we've added on is this sex male coefficient. So we'll talk about how we interpret this, but the idea is that this is kind of like a light switch, where essentially what it's doing is it's adjusting your intercept either up or down. In this case, it's adjusting it up if the professor was male, and this coefficient is 0 if the professor was female, so it kind of just goes away. So the idea here is we're revisiting this, sort of shifting our intercepts, but our slopes are exactly the same across our professors because we have this same slope in our model. If we then transition from this parallel slopes model to a different slopes model, we add a third piece to our model, which is this interaction term between the average beauty and the sex of the professor. So this is where we're allowing for that intercept to differ here by adding on this sex variable, but now we're adding on this piece that allows for our slopes to be different. So this is saying that there is an interaction between this slope and the sex of the professor, so we're allowing for those slopes to change. So we see what we had before. So we have our intercept, We have our original average beauty slope. We have this change in our intercept for being a male professor. And this next piece is our change in our slope for being a male professor. So we'll talk about how we interpret these later, but this is where we're going to adjust this original slope based off of whether the professor is included in this group or not. So whether the professor is male or not, we're going to either keep this original slope or add on another 0.08 if the professor is male. All right, so that is how we fit these different models using our familiar LM function, and we'll talk in the next video about how we interpret these models once we fit them.